So here we are at the beginning of Unit 5. We're going to talk about the atmosphere and climate change. We need to lay like a really solid groundwork for what the atmosphere is and atmospheric pollution so we can understand in Chapter 18 how those atmospheric pollutants are creating global climate change. So let's get started. Here are our goals. We're going to look at the composition, structure, and function of the Earth's atmosphere. We're going to look at the relationship between weather and climate related to atmospheric conditions. We're also going to talk about the reasons for the seasons. That's not on there. We're going to look at outdoor air pollutants and figure out ways to control outdoor air pollution. Stratospheric ozone depletion is another big thing that we talk about in environmental science. So we're going to explain what it is and how we can address it. We're going to look at acid deposition, the consequences of acid deposition and how we're dealing with that. And then we're also going to look at indoor air pollution and see what solutions we have to that. So the case study for this chapter deals with Los Angeles and Mexico City. There's a lot of smog in Los Angeles. I don't know if you've ever seen a picture of the Los Angeles skyline, but very frequently it's like a yellowish, brownish. It's hazy, and that's smog, which is a combination of smoke and fog. They have a huge amount of vehicle exhaust, but the interesting, unique thing about both Los Angeles and Mexico City is that they're in what we call wind-sheltered valleys. They're down in the valleys surrounded by mountain ranges, okay? Mexico City is at a higher elevation than Los Angeles, so because they're at a higher elevation, the atmosphere is thinner, they get more intense solar radiation, so that makes the smog even worse. So air quality is really poor on most days in Mexico City and in Los Angeles. There have been really solid movements in both cities in the last 20 years or so to clear the air. In Mexico City, they shut down an oil refinery. They gave incentives to power plants to move to natural gas rather than burning coal. They got rid of lead from gasoline. That happened here in the 70s, but it took a little longer in Mexico. And they also reduced the sulfur content of the diesel. Reducing all of these things, making all of these changes, reduced the amount of pollutants in the atmosphere, and we're going to talk about how that was. But it continued to grow, even though those measures helped because there were more cars on the road, and there's a lot of stuff that comes out of a tailpipe. So the solution then would be to make changes to the vehicles. So they added catalytic converters for new vehicles, and then in Mexico City, and then they wound up inspecting cars for emissions, which is pretty much all our cars are inspected for now. They plug it into a computer similar to this, and they test, what comes out of the tailpipe. Or they plug it into the computer like in the dashboard and test what's coming out of the tailpipe. They also started to encourage alternatives to cars, public transportation, buses, trains, ride sharing and bicycling. And, 10 years ago or so, there was a lot of pollutant reduction. So these methods work. All right, so let's look at the atmosphere. The atmosphere is the layer of gases that's around the Earth. It's super important to us for a whole bunch of reasons. First of all, it moderates our climate. It's like a blanket over the Earth, okay? So it keeps us warm, whereas the vacuum of space is really cold. Oxygen, we get oxygen from the atmosphere. Super important for all life, plant or animal. It shields us from meteors and hazardous solar radiation. Meteors burn as they come into our atmosphere, so we've reduced meteorite impact. And the magnetic field and these layers of the atmosphere also reduce our exposure to hazardous solar radiation. And the atmosphere, if you go back to our biogeochemical cycles, the atmosphere is an important part of transportation and recycling for water and some of the other nutrients that we talked about when we talked about biogeochemical cycles. It's mostly nitrogen. Okay, if the oxygen content was much higher, we would wind up with spontaneous combustion, and it doesn't happen. So it's mostly nitrogen and oxygen. Water vapor varies, at any given time from 0% to 4%. And this is, what's left. The atmosphere changed as life started to evolve on Earth. When photosynthesis started to happen in these creatures called stromatolites, which we'll talk about in the key points, they converted carbon dioxide into oxygen. And then that led the way for other cellular life that did cellular respiration rather than just glycolysis to develop and survive. So it's really microorganisms in these stromatolites. So the composition of the atmosphere has not always been 78% nitrogen, roughly 21% oxygen, and 0.04% carbon dioxide. The carbon dioxide concentration over time has fluctuated. There have been times when it's been much higher. There have been times when it's been much lower. Okay. But we are beginning to alter some of these quantities of atmospheric gases, particularly carbon dioxide and methane. And we're going to talk about how we're doing that. So what the atmosphere looks like, it's got 4 layers that differ in temperature, density, and composition. So we're really going to look at these first 2 layers, the bottom 2 layers. So the troposphere is where we live. Okay, the troposphere is the bottom layer. It contains the air we breathe, and that's where weather takes place, right? The troposphere gets colder as you move away from the surface of the Earth, okay? And it should make sense. You can see that it goes more negative. It should make sense because you're moving away from the surface of the Earth, and the surface of the Earth radiates heat, right? It's like standing in front of a fire, all right? So as you get further away from the fire, the air is going to be colder. Same thing here, right? As you get further away from the surface of the Earth, the temperature is going to get colder. And it stabilizes at the break between the troposphere and the stratosphere called the tropopause. You don't need to worry about that. The stratosphere, so the vast majority, let's talk about this too before we go to the stratosphere. The vast majority of the gases in the Earth's atmosphere are found in the troposphere because it's closest to the Earth. So you're going to have the greatest gravitational pull. As you get further up, the atmosphere gets a lot thinner. Okay, so the molecules don't have a chance to bump together quite as much. All right. So the stratosphere is our next layer. It's drier. The molecules are spread much further apart, so it's less dense. There's not a whole lot of vertical mixing going on. So we need to talk about this idea of ozone. We're going to talk about ozone in 2 contexts in this chapter. One is ozone in the stratosphere. We call it stratospheric ozone, okay? So it's a layer. There's a higher concentration of ozone here than pretty much anywhere else in the whole atmosphere. We love and rely on stratospheric ozone, okay? Because it absorbs ultraviolet radiation that comes from the sun. There's 3 wavelengths of ultraviolet radiation: UVA, UVB, and UVC. All of the UVC gets absorbed by the ozone layer. All right, UVA and UVB can get through because of the wavelength. All right, so this ozone layer is really important because it protects us from that ultraviolet radiation. I took a meteorology class when I was in grad school, and weather is really hard, really hard to predict because as the temperature and humidity and density and air pressure change, air moves quite a bit. And that's where your weather comes from, right? So the fact that this air moves dynamically in the troposphere makes weather really hard to predict, okay? And here's the statement I said before. Gravity makes the atmosphere more dense at the surface and less dense as you get further up. All right, so atmospheric pressure is the force per unit area produced by a column of air. So if you are standing at sea level, okay, you have a certain amount of air molecules pushing down on you if you picture like this vertical column right up over your head. Okay. When you go up in an airplane or up to the top of a mountain, right, or up a hill of any height, what winds up happening is that you have fewer air molecules pushing down on you, right? Your body is surrounded by fewer air molecules. So your ears pop, right? Because of that difference in pressure outside your head. When you go downhill, or when you go down into a pool, or you scuba dive, or you go down into the ocean, there's more pressure, right? So you feel that pressure on your ears, okay? So your ears pop when you go down too. Awesome. All right, so relative humidity is the ratio of water vapor within the air at a given temperature compared to the maximum amount of water that mass of air at that temperature could hold. So it's basically how saturated the air is compared to how saturated it could be. Okay, so when you walk out of your house in the summertime, and you look at the relative humidity, or you look at your weather app or whatever, and it's like 90% humidity, okay? If you walk out of the house in like July or August, when it's 90% humidity, you can feel the air sitting on your chest. It's hard to breathe, right? If you go out in like, January, February, and the air, the humidity is 90%, it's going to feel a lot different than it will in July and August. Well, why? All right. So chemistry, here we go. When you have warm molecules, a warm substance, right? The warmer the substance gets, typically the more spread out the molecules become, right? So if you have air at 85 degrees, those molecules are going to be spread way out, as opposed to air at like 40 degrees. Those molecules, because the temperature is colder, the molecules are going to be closer together, okay? So if you have air at 85 degrees with 90% relative humidity, 90%, right? That air is holding 90% of the water that it could hold. Those molecules in that warmer air are spread much further apart. So there's a greater capacity, more space, more holes in the sponge to hold that moisture, right? So at 85 degrees, when you go outside in the summertime and it's 90% humidity, you can feel that air, the weight of that air and the weight of that moisture on your chest, because the air is actually heavier. If you would, you took a cubic meter of that air and you weighed it, you could weigh it, it's going to have a greater mass, right, than the air at 40 degrees. Because at 40 degrees, those molecules are closer together. There's not enough space in that 40-degree air to hold as much water. The sponge isn't as holy or able to be saturated. It's not as absorbent. That's the word. Okay, so that's the idea of relative humidity. Important to understand. So since we sweat to cool our bodies, we feel a lot warmer in that higher relative humidity, like July and August, because as we sweat, it doesn't evaporate. Okay, because the air is so full of moisture anyway. All right. This is pretty cool too. The temperature of the air also varies with location and time, as the sun's rays strike some areas more directly than others. And if you guys think about this, this is, where's the picture? There it is. We'll talk about that in a second, okay? So certain areas get more direct sunlight than others, and we're going to talk about that as a connection to the reason for the seasons. So evaporation near the surface, right? Because the surface is warmer, water is going to evaporate. The air is going to be warm and wet, and it's going to create something called convective circulation, okay? This is a really important concept for you guys to understand. Warm air, things that are warm, like the air inside a hot air balloon, are going to be less dense than things that are colder, okay? Warm air, like, go into your house in the summertime. You're not going to go hang out in the attic in the summertime because it's really, really hot. You're going to hang in the basement, right? Because that hot air is going to rise up to the highest parts of your house, and that cool air is going to sink to the lowest parts, all right? So warm air is less dense. It's going to rise and create these vertical currents. That air is going to rise up. As that air rises up, it's going to cool, right? Because the temperature is decreasing as you go up into the atmosphere. And as the air cools, it can't hold on to that moisture, right? Those molecules are getting close together because the temperature is dropping. So that precipitation is going to fall out, and it's going to fall out as rain. So the air is cooler, right? And it's more dense because those molecules are packed together, and it's going to sink, and then the cycle is going to repeat. And here's the picture, right? Here's a great picture. So there's the air picking up the moisture. It's hot, moist air. It rises, it cools, expands, and then it cools. Actually, yeah. And then it's going to rain. Heat's going to get radiated into space because it's further from the heat source. It's going to be cool and dry. It's going to sink, and you're going to get the cycle happening again. Okay? Difference between weather and climate, something really important for you to understand. Weather are the atmospheric conditions in a location over a short period of time, over the course of weeks. So we can have a rainy period, right? A rainy period of weather. Versus climate, which is patterns of atmospheric conditions in a location over much longer periods of time, on the order of years or decades or centuries or millennia. Okay? I like Mark Twain's summary of the difference. Climate is what we expect. Weather is what we get. So, solar energy is the reason why we have seasons on the Earth, right? So sunlight is most intense when it meets the planet's surface at a perpendicular angle, at a 90-degree angle. So what you see is that solar radiation tends to be the most intense near the equator, right? And this makes sense because temperatures are hotter near the equator because it's getting the most direct sunlight versus the poles where the sun is hitting the Earth at an angle, so that radiation is not as strong, so the temperatures aren't going to be as high. So here's the great picture that I was talking about before. So at the equator, the sun is directly overhead. The sun doesn't change the amount of sunlight it produces, the amount of energy that's hitting the Earth's surface. It's just how it's spread out, right? So if the sunlight is directly overhead, all of that solar energy is going to be concentrated in a much smaller area. Okay, so you're going to see more sunlight per unit of surface area. So temperatures here are going to be warmer, okay? Because the Earth is curved, right, the air is going to absorb, the atmosphere is going to absorb more energy because it's taking a longer path through the atmosphere, okay? So it's coming in at an angle, and it's taking a longer path. So what you see here, right, that same amount of solar energy coming from the sun, which is over here, is spread out over a much bigger area, right? So the temperatures are going to be cooler at the poles versus the equator. Something else we need to know about is that the Earth is tilted on its axis by 23.5 degrees. So for half of the year, a hemisphere is tilted towards the sun, and then for the other half of the year, a hemisphere is tilted away from the sun. Really amazing picture, okay? This is a really, really, really great picture. So let's do September, right? So equinoxes, right? Equinox literally means equal night, okay? So in this case, in the September equinox, the equator faces the sun. Here's the axis, the axis of the Earth, and there's the tilt from 23.5 degrees away from vertical, right? So the axis points in the same direction in every instance of the Earth here, at every point in the year, okay? So in this case, in the September equinox, neither hemisphere is tilted towards the sun. The equator faces the sun directly. Neither pole tilts. You get 12 hours of darkness and 12 hours of daylight. Equinox, equal night, all right? If we go round to December, right, if you draw a line right here, well, equatorial's down a little further, right? If you draw a line at the equator right about here, the northern hemisphere is tilted away from the sun. right? So when the northern hemisphere is tilted away from the sun, it's getting less direct sunlight. So that means it's going to be cooler, right? So this is the December in the northern hemisphere. It is winter, the beginning of winter, the winter solstice, okay? The opposite thing happens in the southern hemisphere. This is the summer solstice. So when we are getting ready to celebrate Christmas in the northern hemisphere, they're still celebrating Christmas in the southern hemisphere too, but it's the middle of summer, okay? Which is weird. Okay, so fast forward a few months, March equinox. This is our spring equinox. Again, neither hemisphere is tilted towards the sun. It's the equator that faces the sun. So again, equinox, equal night, the same amount of hours of daylight and darkness. And then fast forward to right around the time school ends. Okay, in this case, you see that the axis is still pointing in the same direction. But in this case, if we draw the equator right about here, the northern hemisphere is tilted towards the sun. So this is summer in the northern hemisphere and the beginning of winter in the southern hemisphere. And then we roll back in to the fall equinox. So we know this. Air generally becomes colder as altitude increases, right? Molecules are not bumping together as much, right? The molecules are more spread out, so temperature decreases. So when that happens, right, you have the heat that radiates up from the surface. You have this really great vertical mixing, right? That warm air rises up. And in an urban area, when that warm air rises up, it takes all of the pollutants with it. It's fabulous, okay? So when you have good winds and a warmer at the surface, then up into the atmosphere, those pollutants go away. What winds up happening in some cases, like in Mexico City and in Los Angeles, the pollution winds up getting trapped. Why does that happen? Okay, when you get something called a temperature inversion. Inversion means upside down. So the temperature profile of the atmosphere is upside down. The cool air is trapped beneath the warm air. Okay, we know that cold air sinks because it's more dense, and warm air rises because it's less dense. Okay, this cool air is not going to rise because it's cool. So what you wind up getting is you don't get that vertical mixing. That happens really frequently when you have cities or areas that are in valleys, like Mexico City and like Los Angeles. The mountains that are around here stop the sun. When the sun starts to rise, typically what winds up happening in a city that's not surrounded by mountains is that the lower part of the city warms up, right, faster than the upper part, because it comes up and hits the lower angles and then moves up and sets on the other side. But the mountains block that sun from getting to the lower part of the atmosphere near the city. So it warms the upper atmosphere first, and then the lower atmosphere stays cool. Eventually, that lower atmosphere is going to warm as the sun gets higher in the sky and rises up over the mountains. But morning air quality in cities like Mexico City and Los Angeles are really bad because that air, the bottom air is cool. It's not going to rise and take all the pollution with it. So you get this thing called a temperature inversion that creates an inversion layer where the pollution doesn't mix out. Okay, it's going to be important for you guys to know these cells, all right? So Hadley cells are the cells near the equator. The Ferrel cells are the cells in the middle. And then the polar cells are cells that are up by the poles, okay? So what winds up happening here, right? You're getting the most direct radiation from the sun at the equator. So the air is going to rise and convection is going to happen. It's going to sink, right? It's going to cool and it's going to sink. If you look at the geographic locations of most of the deserts on the planet, they're located around 30 degrees north and south latitude. Why? Because there's cool, dry air sinking. You're not going to get precipitation happening if you have air falling, right? So it's low pressure systems on the weather maps that you see, or when you see a lot of precipitation, there's air rising, so it cools and condenses to make precipitation. All right, so it sinks and then it warms again, and then you're going to get warmer air rising, not super warm because we're at 60 degrees north latitude. It's kind of chilly up there, but you're also going to wind up with a lot of precipitation going on here, right? This is, if you've ever seen The Perfect Storm or anything like that, The Day After Tomorrow, this is where those storms originated from. And then as the air gets cool again, it's going to sink, right? If we think about our deserts here at 30 degrees north and south latitude, the tundra, which we called the frozen desert, is located at the poles, north and south. Why does that make sense? Well, because the air is sinking here, much like here, and there's not going to be much precipitation. It just happens to be really cold. Pretty cool. All right, so this area right along the equator doesn't really receive wind. It's called the doldrums. A lot of, explorers in the 15 and 1600s, if they crossed the equator, they wound up getting stuck in the doldrums, and they would wind up with all sorts of depression and issues because they were wind-blown sailing ships. If they got stuck in here, it was pretty problematic. We talked about El Nino. We did talk about El Nino. So these are the winds that create that circulation in the Pacific to allow El Nino to happen. When the trade winds blow harder from the eastern Pacific to the western Pacific, you wind up getting La Nina. When they slack, when they don't blow as hard, you wind up getting El Nino. Okay, we live in the westerlies, right, between 30 and 60 degrees latitude, both north and south, because the winds blow from the west. Winds are named for the direction from which they blow. So these are the northeast trade winds because they come from the northeast. And these are the southeast trade winds because they come from the southeast. Hurricanes happen when you've got low pressure systems having access to warm, moist air from tropical oceans. You don't really get too many subtropical hurricanes, although that is changing as the climate is changing. Coriolis effect, which we will talk about, causes hurricanes to move counterclockwise in the northern hemisphere. So they spin this way. So why do hurricanes have so much rain? It's a low pressure system, right? Low pressure means rising air, and it's rising air that's full of moisture from the warm ocean. So there's a lot of evaporation. So you get this really huge, massive rainstorm with a lot of heavy wind. Tornadoes happen typically where you have air masses bumping against each other when they are really different, right? So you get a lot of them in the Great Plains states when you've got that cold air coming down from Canada and the warm air coming up from the Gulf of Mexico. They collide. Convection starts to happen, and it can cause rotation like you see in the picture. All right, so let's talk about air quality. Captain Obvious statement, the first two things that we see. Air pollutants are any gases and particulate matter that get added to the atmosphere that can affect climate or harm people and other living things. And when you release air pollutants, you create air pollution. Ta-da! We've done a lot here in the United States and around the world in terms of improving technology and creating public policy to reduce most kind of outdoor air pollution outside in the industrialized nations. But air pollution is natural, okay? Fires occur naturally, right? So forest fires are going to put up ash and particulate matter and carbon dioxide as well when they burn. We talked about this when we as humans encroach into these native ecosystems that tend to be fire prone, and then not doing the prescribed burns, allowing fire suppression to take place. Another kind of air pollution is dust, right? We've got these winds that come off of Africa and they bring lots of dust. You can look at satellite images of dust blowing off of Africa. It's kind of crazy. It's gotten a lot worse because there are unsustainable farming and grazing practices that can degrade soil to basically expand the desert. Volcanic eruptions. Mount St. Helens, 1980. Volcanic eruptions release particulate matter and sulfur into the atmosphere. Particulate matter meaning ash, right? This is a huge plume of ash and cinders and also sulfur dioxide. So if you are surrounded by ash, right, it can ground planes because the ash is so hot, it will actually melt to the engines of airplanes or clog up the engines so they can't fly, they can't take off. It can also damage car engines, so your intake filters won't get air, they'll get clogged by ash, and it can cause respiratory illnesses. Volcanic ash is really sharp. It's not like fireplace ash that's really soft. It's little bits of like glass almost. So if you breathe that into your lungs, if it's not going to shred your mucous membranes, from your nose down into your lungs, once it gets down into your lungs, it's going to basically turn to cement. So it's really not pleasant. Long term, this stuff getting up into the atmosphere, the sulfur dioxide, as well as the ash, right, can get up into the atmosphere. Ash forms a physical barrier, so it does not allow the sunlight to penetrate the atmosphere. It instead reflects the sunlight or absorbs the sunlight, depending on how dark the ash is. So that sunlight is not going to make it to Earth. If sulfur dioxide reacts with water and oxygen to form aerosols of sulfuric acid in the atmosphere, it is going to block sunlight. So sunlight doesn't get through. After Krakatoa or Tambora erupted over in Indonesia, it put so much sulfur dioxide into the atmosphere. That summer, they had appreciable, measurable snow in New England in June and July and August. After Mount St. Helens erupted in 1980, in the winter of 1981 into 1982, when I was little, I very clearly remember an Easter picture, that my mom took of my brother and I. We were standing on the 15-foot plowed up snowbank that my dad had plowed from the weather that winter. We had had so much snow. So it does actually do that. We create, there's anthropogenic, let's throw that word out, air pollution, outdoor air pollution. So if you have a pollutant that is directly released from a source, you can pinpoint it. You know exactly where it's coming from. It's called a primary pollutant, right? So some examples: ash from a volcano, sulfur dioxide from a power plant, or carbon monoxide from a car. Those are all examples of primary pollutants. If you take primary pollutants that react with each other or things in the atmosphere like oxygen and water vapor, they form secondary pollutants, okay? Ozone is formed as a result of primary pollutants getting together in smog. Sulfuric acid is another example, okay? So residence time is how long the pollutant is in the atmosphere before it settles to the ground. So typically the longer the residence time, the longer term the effects are, right? So these are our greenhouse gases, okay, and ozone depleters. The longer they're in the atmosphere, right? Residence time of centuries. They can cause major issues around the globe. Whereas something like sulfur dioxide or your particulate matter, it'll be up for a while, and then it'll come down, right? So it doesn't stay in the atmosphere quite as long. So we talked about the Clean Water Act. Now we're going to talk about the Clean Air Act, all right? Clean Air Act was another law passed in the 60s that was amended a couple times. That does a few things. It funds pollution control research, sets standards for air quality, and encourages emission standards for automobiles and other point sources. Remember, a point source pollutant is one pinpointable source. We, in our, as part of the Clean Air Act, individual states are required to monitor emissions for air quality. Okay, so New Jersey's emissions standards are higher than Pennsylvania's emissions standards, right? You have certain places, you can take your car to like a garage and get inspected, whereas here in New Jersey, you can't. So they set the standards and develop and implement and enforce their own regulations. Okay, so that's why different states have different rules about inspection and what counts as passing inspection and what doesn't. So there are 6 major pollutants that the EPA, states and local agencies monitor and then have to report to the EPA. So it's carbon monoxide, sulfur dioxide, NOx, which are nitrous oxides. You can also call this SOx. VOCs, or volatile organic compounds. PM, which is particulate matter, and ammonia. So carbon monoxide is colorless and odorless, and it is produced by the incomplete combustion of fuel. So it comes out of a tailpipe, all right? Vehicles and engines are the biggest sources. That's why you're never supposed to start your car in the garage with the door shut, because carbon monoxide will build up. And it binds to hemoglobin, which is the protein in your blood that transports oxygen. It hops in to the spot where oxygen is supposed to go, okay? It bumps oxygen out of the way, and then you get carbon monoxide into your system. And carbon monoxide doesn't pick up electrons at the end of the electron transport chain in aerobic cellular respiration. So it's not going to work, okay? And this is why you wind up dying as a result of carbon monoxide poisoning. NOxes are nitrogen compounds, nitric oxide and nitrogen dioxide. They are also produced when nitrogen and oxygen combine during combustion in engines. NOx emissions contribute to smog, acid deposition. We're going to talk about how it contributes to smog in a little bit. Acid deposition, it forms when you've got the NOx emissions coming out and combining with oxygen and water vapor to make nitric acid. And it's also a factor in ozone depletion. Volatile organic compounds, they're carbon-containing chemicals. They come out of tailpipes, but they also are like that new car smell, or the smell when you print something on a printer and you get that smell out of the printer. Those are VOCs, okay? Volatile organic compounds that come out of tailpipes will react to produce secondary pollutants like smog. Particulate matter, okay? Particulate matter is solid or liquid particles that can be aerosols that are small enough to be suspended into the air. So some primary pollutant examples are dust and soot, like volcanic ash, or secondary pollutant examples are sulfates and nitrates, right? They classify particulate matter by size. PM10 particles are less than 10 microns in diameter, so 10 millionths of a meter in diameter. PM 2.5 particles are less than 2.5 microns, right? PM 2.5 particles are more dangerous than PM 10 because PM 2.5, because they're so small, they can get down into your lungs, right, and cause issues and clog up your alveoli, right? So you have your esophagus, which comes down out of your throat, right, branches down into your lungs, to your bronchi, and then your bronchioles branch off that, and your bronchioles get into the alveoli. Those are the little tiny sacs where the capillaries run, where gas exchange takes place, okay? PM 2.5 is small enough to get into those alveoli and prevent gas exchange from taking place, which is problematic. Lead is a heavy metal. We talked about this when we talked about air pollution from mining back in the 70s and before. They burned leaded gasoline. So it would be vaporized. It would come out of tailpipes or as the result of metal smelting. It accumulates in the body and it causes some pretty severe nervous system malfunctions. So you definitely don't want lead in your system if you can avoid it. So a lot of our, those monitored air pollutants have decreased significantly since the Clean Air Act was passed, right? This has happened even though we've had a lot more, the population has gone up, vehicle miles traveled has gone up, and GDP, our disposable income essentially has gone up quite a bit too. So we have more driving and more people and more money to allow us to drive, but we've still decreased a lot of those pollutants. How do we do that? Okay, we talked about baghouse filters a little bit, right? We scrub the gases, right? They, as you burn energy, fuel for energy, that kind of thing, coal or whatever you're burning, it's going to give off gas, right? So that's going to enter the scrubber. The gas is going to get wetted, right, by this chemically treated water. That's going to allow those materials to precipitate out, right? That mist is going to capture the pollutants. It's going to bring them to the bottom. The purified air is going to exit the stack. And then all of those sludge pollutants are going to have to go to a hazardous waste dump. So scrubbers chemically and physically remove those pollutants. Catalytic converters are really expensive because they contain metals that react with the stuff that comes out of internal combustion, right? The hydrocarbons, the carbon monoxide, and the NOx, and converts them to carbon dioxide, water vapor, and nitrogen gas. What comes out of the tailpipe, right, thanks to the catalytic converter, is a lot cleaner than what goes into the catalytic converter, right? If you remove your catalytic converter, you're going to have major pollution issues, emissions issues, okay? Here's why. You got metals in this honeycomb, right, which increases your surface area for those gases to pass through. Rather than it being like smooth on the inside, it's a honeycomb. Look at these metals. Palladium, rhodium, and platinum, super expensive metals. That's why catalytic converters are really expensive, because they're coated in these precious metals, right? These valuable metals. So what goes in? These are your chemical reactions. What comes out? Oh, the chemical reactions. What goes in? These chemical reactions happen, and then this comes out. We looked at those criteria pollutants, right? Each pollutant has what they call an ambient air quality standard. So it's the amount that can be in the air. Okay. We talked about nitrogen dioxide. It's reddish brown. Okay. It is not very nice smelling, and it contributes to smog and acid precipitation. We talked about stratospheric ozone, right? And that's the layer of ozone up in the stratosphere. That is our friend. This is tropospheric ozone, or ground level ozone. This is not our friend, okay? It's a secondary pollutant that's created by the reaction of NOx and VOCs in sunlight. And we're going to see a picture of that hopefully in a minute. If not, I'll make sure I get it to you. Ozone is unstable. It is actually more dense than oxygen, and it doesn't allow for gas exchange to take place. So it can cause issues and respiratory problems. So if there are ozone action days, if you ever watch the weather in the summer, you are not supposed to be out on ozone action days, especially if you are really old, really young, have lung issues, or if you have stuff like asthma, okay? And we can look at the air quality, the World Air Quality Index, WAQI.info, to see these monitoring stations that take daily or hourly air samples. So most urban areas, you know, in the 40 years between 1985 and 2015 have gotten better, right? So Memphis was pretty high in 1985, but is a lot lower now. Miami was never really all that high, but it's like nothing now. Boston, Philadelphia, etc. Los Angeles has 106 days every year as of 2015 that are still considered unhealthy air days, right? So it's not great, but it's better than what it was. There are toxic air pollutants, okay, that can cause cancer, reproductive defects, neurological, developmental, immune system, respiratory problems. Okay, mercury is one of them that comes from a coal-burning power plant, which we talked about when we talked about biomagnification and bioaccumulation. VOCs from gasoline, and methylene chloride, which is found in paint stripper. So it is not necessarily true to say that only people that live in cities are at risk for issues related to air pollution, okay? Out in the country, out in rural areas, you wind up with potential exposure to air pollution too. So airborne pesticides from farms, right? If they spray pesticides or herbicides at the farm near your house, you're going to breathe that stuff in. Industrial pollutants that drift from distant cities. So winds move air, we know that. As the winds move the air, they don't just move the air, they take everything that's in the air, the SOx, the NOx, the VOCs, all that stuff. So you might not be creating the pollution, but you are suffering from the effects of that pollution. All right, methane, hydrogen sulfide, and ammonia from animal waste in large feedlots. It's kind of smelly. And if you live anywhere near a fracking site, you can be exposed to those fumes as well. Air pollution is more of an issue in industrializing or developing nations rather than industrialized nations, okay? As these nations move across the demographic transition, right? They're in that transitional into the industrialized phase. They are expanding rapidly. They're using factories and power plants, cars, and they're using wood, charcoal, and coal for cooking and heating their homes, right? So the technology that winds up getting to these developing countries is polluting technology. It's dirty technology. It's really outdated, but it's what they can get their hands on, right? Because it's cheap and it's quick to build, and it can help them move across that demographic transition to keep up with the Joneses, so to speak. But the problem with it is that these nations are causing major air pollution issues as a result. So in Beijing, pollution became so severe that people were outside in the air wearing masks. Okay, the air quality index goes up to 500, was up over 755. And the World Air Quality Index.info, WAQI.info, if you look at it, China on any given day, it's like 800 or more. When I taught this class right before we went out with the pandemic, we had looked at, we were covering this chapter right beforehand, and I pulled up, WAQI.info, and China was like green and yellow, which means there's like no pollution. And it was the first time I had ever seen that, ever. I'm upset with myself that I didn't take a screenshot, but it was just kind of crazy. Pollution levels in major, typically Asian, because that's where most of the development is, cities like Delhi, okay, in India, have some of the worst air pollution levels. And like this is the air that people are breathing out there. 2018 WHO survey, 11 of the 20 most polluted cities on Earth are in India. And eventually that population is going to surpass China's population. So I don't see that getting better. All right, let's talk about smog. Smog is smoke and fog, right? It's a general term for a mix of air pollutants that accumulates as a result of burning fossil fuels, especially when you have a lot of vehicle traffic, right? So there's two kinds of smog. One is industrial smog. Industrial smog is the result of industry, right, rather than tailpipes. So it contains carbon dioxide, carbon monoxide, mercury, sulfur, all from burning fossil fuels, okay? So coal and oil in particular, you burn them for industry, you get particulate matter coming out, right? Sulfur dioxide, that's a primary pollutant. Sulfur dioxide is also a primary pollutant, right? When you combine that with oxygen and water vapor that's already in the atmosphere, you can get the secondary pollutant of sulfuric acid, okay? This stuff can then be blown over large distances and create acid deposition really far away from this source. The worst industrial smog event happened in Donora, Pennsylvania in 1948. It was in a really small valley, right? So you're going to get that temperature inversion. And it wound up trapping smog from a local factory in that valley for days. Okay, and that's noon in Donora in the middle of its 1948 smog event. That's crazy. London had a similar killer smog event in 1952. A lot of people died from asthma issues and breathing issues. And that was the first season of The Crown, I believe. They talked about it. The other kind of smog we can talk about is photochemical smog. Photochemical is these chemicals that particularly come out of tailpipes reacting with light, right? So photochemical smog requires light. It's when sunlight makes these chemical reactions happen between primary pollutants and things that are already in the atmosphere, producing a whole bunch of really nasty chemicals, right? Ozone is the most abundant that comes as a result of it. And the fact that there's nitric oxide in the atmosphere, this is Los Angeles, by the way, gives the smog like a brownish haze, like you can see here. Los Angeles is in a valley, so if there's not a whole lot of wind, it's really warm and it's sunny, it's like the perfect mix to make photochemical smog. And here's how it happens, right? You burn these hydrocarbons, you get nitrogen dioxide, nitric oxide, and VOCs in the presence of solar radiation, okay? Oxygen gets added and you wind up with ozone, okay? And you get all of these nasty, nasty things as a result. How can we reduce smog? Well, we want to. A lot of it has to take place, those steps have to take place at the state and local level. Federal level. So you put restrictions on emissions, you put caps on emissions from power plants, refineries, factories, right? You make sure you require vehicle inspections, and you improve technology on cars, right? You make them more efficient. So Los Angeles drivers currently burn 2.7 times more gasoline, but smog levels have gone down quite a bit, right? Ozone levels are still a little too high, but air quality has gotten a lot better for those reasons that we talked about in the previous slide. A big conversation now, should we start to regulate greenhouse gases as pollutants? And it's kind of gone back and forth over the course of time. Supreme Court said that, yes, the EPA can regulate greenhouse gases, right? So then they introduced carbon emission standards rather than the fuel efficiency standards, just the CAF standards, for cars and trucks, and then set it for power plants. And then the EPA tried to issue or launch a clean power plan, which gave states options and therefore incentives for reducing carbon emissions. But the Supreme Court said, nope, we can't do it. And then Trump took it apart. So there's that. All right, let's talk about ozone. Ozone is really great up in the stratosphere, right? We love ozone in the stratosphere. Ozone is our friend. But in the 80s, we found that there were chemicals that humans created, big surprise, that we call ozone depleting substances that were causing that ozone to thin and degrade. Okay, the biggest ozone depleting group of chemicals were halocarbons, right? So when you take a hydrocarbon, right, and instead of replacing the hydrogen, right, with it, you put carbon around chlorine, fluorine, or bromine. And one really particular group of those halocarbons, the chlorofluorocarbons, or CFCs, were used as propellants, right, in hairspray, spray cans, fire extinguishers, refrigerators, air conditioners, those kinds of things. So what do? Why are CFCs a problem? All right. So down on the surface, they don't seem to cause any problem, right? They're non-reactive. But when it gets up into the stratosphere, right, those chlorines are popped off the carbon, right? When that happens, chlorine is more electronegative. It wants those oxygen atoms more than the oxygen atoms. Right? So chlorine has the power to pull one of those oxygen atoms off of ozone and create chlorine monoxide. Okay? So chlorine pulls ozone apart. So then the ozone layer winds up getting depleted, right? To the point where you get a hole in the ozone, right? They discovered it in the 80s over Antarctica. When you have winds in the stratosphere, it causes those pollutants to concentrate over the poles. Those gases would stay there and then break down in the spring when the sun, broke up the clouds. So we were so worried about CFCs and ozone depletion that we all sat down, many of the countries on the earth, sat down and signed the Montreal Protocol. Right, so the Montreal Protocol, another piece of legislation you need to know, dealt with ozone depletion. So they dropped the ozone-destroying potential chemicals over time, right? So we started off with CFCs to be cut in half by 1998. And as we've gone on through time, we have increased the number of halocarbons that were on the restricted list. So we're really in pretty good shape compared to where we were in the early to mid 80s. Right? We think that the ozone layer is going to recover completely back to normal sometime after 2060, because some of these things have a longer residence time. All right, let's talk about acid deposition. It's Captain Obvious, the deposition of acid or acid-forming pollutants from the Earth's atmosphere onto the surface, right? So we've had some success in dealing with these globally. When we look at acid precipitation or acid deposition, it's not just rain, right? We think about acid rain. When we were at the Rosemont Cemetery, we looked at why the limestone headstones were eroding, and we figured out that the winds and the weather comes from the west, and precipitation around here is a little on the acidic side. So that's why you wind up with degraded limestone headstones, okay? You could have acid rain, fog, gases, or dry acidic deposition as a result of these acids getting up into the atmosphere. So how does it happen? Okay, and I've kind of alluded to this a few times. So you have SOx and NOx, okay, getting released from tailpipes and urban areas and industry, right, factories. Those are your primary pollutants. They combine with water and oxygen typically to create sulfuric acid and nitric acid. If you look, the winds blow these particles away from their source. So you wind up with acid deposition pretty far away from where the stuff came out of the tailpipe and the smokestack. So upstate New York has a lot of dead lakes in the Adirondacks because of industry in the 40s and the 50s and the 60s, pre-Clean Air Act, getting up, producing the SOx and the NOx, getting it up into the atmosphere, and then it moving with the winds from like Toledo and Chicago and all that stuff, moving to the east from the west, the way the winds blow, to drop acid deposition, particularly acid rain. So this is what I just talked about. It's got a lot of issues when it comes to ecosystems, right? Here, acidified 41% of Adirondack, New York lakes, 15% of New England lakes. It also erodes a lot of stone buildings. This looks very familiar. Before acid rain and after acid rain, these limestone obelisks cause issues. They also, acid deposition also damages crops because plants need a certain pH level in order to have their enzymes work. Get outside that pH level, too low, too high, those plants are not going to survive. So we're dealing with acid precipitation. The amendment to the Clean Air Act that was passed in 1990 really set up a solid solution to acid precipitation and acid deposition. They set up this cap and trade program, which is actually kind of cool, to allow permits for sulfur dioxide pollution, right? And if you stay below that limit, you can trade your extra allowances, which created a huge economic incentive to reduce those emissions. So really, like if you think about it, if you invest in that technology to reduce your sulfur dioxide emissions, then you can sell your extra shares of sulfur dioxide to a company at quite a hefty price. And it did a really good job in reducing sulfur dioxide emissions. So if we look at the NOx part, right, the nitrous oxide stuff, we've put some solid regulations and restrictions in place to prevent NOx from coming out as much, which is going to reduce that nitric acid deposition. So we've had, historically, back in the early 90s, a pH of our precipitation like less than 4.5. Typical rainwater pH is about 5.5 or so somewhere around here. As a result of the amendment to the Clean Air Act, as of 2017, it's gotten a lot closer to basic, which is kind of where we want to be. All right, so that's all outdoor air pollution. We're going to talk about indoor air pollution. Believe it or not, there's quite a lot of indoor air pollution. It's in a greater concentration. That's mostly because when we really looked at increasing energy efficiency in the 1970s, we wound up, sealing up our buildings really well, windows that don't open, like a lot of the office buildings. They don't have windows that open because it reduces energy consumption, but it also does not allow airflow, right? And airflow is what allows those pollutants to move. So in the developing world, right, typically the biggest pollutants in the developing world are particulate matter, right? Because people are burning wood, charcoal, animal dung, or crop waste. They're burning biomass in their homes, right? So this person is breathing in this particulate matter and ash and soot, right? They're cooking with it, they're heating their homes with it. So that particulate matter pollution is often 20 times higher than what the EPA says it should be. Here in the industrialized world, smoking is an issue, right? E-cigarettes and vapes can also expose people to VOCs, fine particulates that get down into those lungs and don't allow gas exchange to take place, and heavy metals. Radon. Radon's a big thing where we live, right up in here. It's colorless and odorless, and it exists in a lot of low basements, not low basements, low-lying areas, particularly basements in our houses, as a result of natural decay of radioactive elements, particularly uranium, in soil and rock, right? It is odorless it is colorless. So you don't know if you have radon in your basement. You have to get it tested, okay? And it varies from region to region depending on the kind of rock you have. The older rock, which is typically in the northern part of the United States and in the spine of the Appalachians here, tends to be where you have a lot of radon. We are exposed to lots of VOCs, okay, these volatile organic compounds, because it's that smell that's released by plastic, oils, paint, laser printers, new carpeting, fax machines, all that stuff. And it's really kind of hard to pinpoint the effects that chronic VOC exposure can have because you are exposed to lots of different VOCs in low concentrations over long periods of time. And you don't know like what the cocktail mix is going to be to cause issues. So here are some examples of how the different kinds of VOCs that you see in your house, around your house. So things that we can do to enhance indoor air quality. If we look at the developing world, you dry your wood before you burn it rather than burning smoky wood. Cook outside rather than cooking inside. If you have the means, shift away from biomass and use less polluting fuels such as natural gas. Or do something to increase ventilation, a hood, a chimney, a window, right? So you don't have all of that polluted air trapped in your house, okay? In the developed world, if you look at our exposures, okay, don't smoke, don't vape. You can test, get your house tested for radon. When we built our house, because of where we live, we had to have a radon ventilation system installed. I very clearly remember my parents getting our house tested for radon in the basement in the 80s, right? And then fortunately we were okay, so we didn't have to put in a radon remediation system or a radon ventilation system. And then just minimize your exposures to VOCs. You can buy low VOC paint and low VOC printers and toner and all that kind of stuff. All right, we've now established a pretty solid base for what's going on in the atmosphere. And then we're going to look at climate change.